So this exam is going to be covering chemistry. Now, I did not give you a homework assignment for this week simply so that you would be able to vote time to study, but you should do some problems from those sections because they won't be ignored on the test. I just didn't want to, assign things and have students like, I didn't have time to study for the test because I was doing the homework. Right, because you know how that goes. Yeah. So we're doing chapters 12 through 19, and so just some brief comments on each of the chapters. And if you look at the review that I put on Moodle, it has a lot more words than what I have in the slides. Excuse me?
Is this on Moodle?
This will be on Moodle as well. The review is already on Moodle. So chapter 12 was basically an introduction to what atoms are. So we learned things that you probably already knew, that atoms have protons and neutrons in the nucleus and electrons that orbit around it. Some things that I'm sure you didn't know, things like that we have no idea what the path is that an electron takes when it orbits in the atom. We just can calculate where it's likely to be. And then we talked about the organization of that periodic table. Now, the periodic table will be back there. I'll probably give you a photocopy of a periodic table with the exam as well. Right? I don't want you to have to memorize, what is the atomic number for scandium? I don't even know what the abbreviation is. Well, you don't have to know the abbreviation for scandium either. Right? But I want you to have that kind of information to be able to use it. So for the periodic table, we have different behaviors on the columns. The periodic table, as we know it, was initially designed by Dmitri Mendeleev, so we call it the Mendeleevian table. I really wish that Julius Lothar Meyer's table was the one we chose simply because then we could call it the Lothar table and it'd be more fun. So the design there, the first column, all behave similarly in chemical reactions. Now that we have better understanding, why do they behave similarly if they're in the first column? They have one.
They are in the same group.
Yeah, they're in the same group.
Which means they have similar properties. They have the same outer electron.
Right, they have
Yes.
one valence electron. That's the key there. That's why they behave similarly. As you go across, the masses increase. Basically, the design is, with Mendeleev, he just did it by the masses and the chemical properties. Today, we do it with quantum mechanics. But the first column all has one valence electron. And what do we call the elements in the first column? Alkaline metals. So those are the alkaline metals. Hydrogen, hey, it's a metal. Who knew hydrogen was a metal? Hydrogen can exist in a liquid metallic state, believe it or not. Lithium, sodium, potassium. We don't often think of those as metals, but they're alkaline metals. The second column, what does the second column have in common?
They're also alkaline.
They're actually alkaline earth metals.
What's the difference?
Well, the difference, it comes from where they're found in making bonds, what kind of materials they're found in. And that's about all I know. Remember, I'm not a chemist myself. But the fundamental difference in why they're two second column instead of the first column is because they have two valence electrons. Now, there is one element that's not in that second column with two valence electrons. Which one's that?
Wait, it should be in that column and it's not?
Yep, you see some periodic tables that has an element shown two places. Helium. Because helium also has two valence electrons.
Why do they move it to?
Okay, so why they moved it across is because in the first shell, how many electrons can you have? Two. And so helium has a completed shell. In the right column, the noble gases are the ones that have completed shells. And so helium really belongs in two places. And we default to putting it in the right-hand column because it behaves more like a noble gas than it does like and alkali earth metal. Okay, then between columns 2 and 13, what do we call those elements? Yeah, transition metals. Those are the ones that we usually think of as metals, right? Everybody says, yes, iron, that's a metal. Gold, that's a metal. Those are the transition metals. And as I talked about in class, what's going on there is that electrons are filling if you're on the fourth period, that's the fourth line, the electrons are actually filling third period energy levels. And so the properties aren't changing very much as you put more electrons in. Then we get to 13, don't really have a name for columns 13 or 14 or 15. Column 16 has a name. I'm not going to ask you that on the test. You do not have to worry about memorizing chalcogens, I think is what it is. I looked it up last night to make sure I'd have it right. Even though I'm not requiring you to memorize it, why shouldn't I? So those, then the last few do memorize. What do we call the column that has fluorine, chlorine, bromine, iodine? They're the halogens. What's special about the halogens? The what? I'm sure that was a joke.
Oh, I didn't see.
They have their electron shells filled, so they're not very reactive.
Actually, the halogens is one before that. So they're one short of having it filled. So they're very reactive, right? Because, as we learned, you have a lower energy state when you have a completed shell. And so the halogens are one short of having a completed shell. They really want another electron. What do we call it? They really want another electron? You have a high electronegativity. So, like fluorine is our highest electronegativity atom. Electronegativity is largest in the top right corner, lowest in the bottom left corner. The left column, they have one extra electron, they're happy to give it up. Right column, they're missing one, they really want more. So you should know those columns, the differences. Yeah, that's what I have down there at the bottom is have that. You don't have to memorize the elements or anything like that, but you should be able to identify the valence. So if I look up there and I see, let's say boron, capital B, how many valence electrons does that have? 3. And how do you know it has 3? Yeah, 1, 2, gap for the transition metals, 3. That's exactly how you get it, right? It's not tough stuff. You just have to know, well, this is how you get it. Okay, so that was chapter 12. I got a couple more things here. Quantum theory came up in chapter 12. Quantum theory means we have specific steps. You guys remember when I got out those little glasses and we looked at a filament that was hot and we saw rainbow colors, continuous colors. But then when we took the gas and we looked at the gas that was excited, we saw only specific colors. Those specific colors are indicative of what we say quantized energy states. There's only certain energy states something can have, not continuous states. And so the development of the atomic models, we went from first I'm going to get epilepsy watching that picture. Well, not going to get epilepsy. If you're epileptic, it'll cause you to have a seizure. You don't gain epilepsy by watching this. So we started with, the atomic model that just said you cut things up, and, Democritus said eventually you're going to get to the smallest piece, and you can't cut into anything smaller. But then we had the realization that electrons were in material, and so the theory of the plum pudding model, positive charge everywhere with little electrons. Then the experiment with the gold foil showed that you have a very massive piece of positive charge. And so we had the planetary model with a positive nucleus that's massive and then electrons orbiting it. But then because the energies have these discrete levels that we saw with the lamp, we shifted to a quantum model. And that's where we are today with a quantum model that says that you can only have, 2 electrons in the first shell and 8 electrons in the second shell. And It's actually 18 in the third shell, but as we said, you don't put in the next 10 until you get down to the fourth. That's chapter 12. Going to chapter 13. Focus sesame. So in chapter 13, we started talking about radioactivity. Radioactivity, it's important that you know radioactivity is coming from the nucleus of atoms. It occurs because the nucleus is not in its lowest energy configuration. It's unstable. Remember the example of taking like a pin and balancing it. You can balance it with just a little bump, and it falls to a lower energy level, and it gives off energy. You hear a sound. Well, that's what's going on with radioactive nuclei. They're not in a stable configuration. You give it a little bump, and it falls to a more stable configuration and gives off some energy. And that energy could be in a number of things. The three that you're responsible for knowing are an alpha particle, a beta particle, or gamma. Alpha particles, that's 2 protons and 2 neutrons, what we now understand as a helium nucleus, that comes out of the nucleus. So if I have something like uranium-238, and an alpha particle comes out of that nucleus, it lost 2 protons, it lost 2 neutrons, so the 238 is going to go to 234, because that 238 is the total number of things in the nucleus. You took 4 out, so there's 4 less, 234. And the number of protons drops by 2, so it's going to go from uranium to thorium. So that's a transmutation, a changing of the element when it undergoes radioactive decay. You could also have a beta minus decay, which is an electron coming out of the nucleus. And I really emphasize there are no electrons in the nucleus. So this electron that comes out of the nucleus actually is created in the decay. And yeah, they say, whoa, like, how do you create electrons? Mass is a form of energy, and you're having mass being absorbed, and something has to disappear for this to appear. But you're creating these new particles. So the electron comes out, but when the electron comes out, it takes away a negative charge, which leaves the nucleus with a more positive charge. So if I have something like cesium, if cesium gives off a beta decay, an electron leaves, it's going to have 1 more proton in the nucleus, so it's going to become barium. CS and Ba. So that's a beta decay, and then the gamma decays, it's just electromagnetic radiation coming out. It's not a particle in the classical sense, but in the quantum sense it is, because in quantum theory we come to a duality with light. The light is both a wave and a particle with no mass. And so you can talk about a gamma particle as the particle of light, a photon, but it has no mass, so we don't think of it, it's not a classical particle. So there's no change in the nucleus in terms of number of protons or number of neutrons when you have a gamma decay. It's just a change in the energy of that nucleus. And the energy difference is taken out in the gamma particle that leaves. So those are the 3 types of radiation that you need to know about. You should know about shielding. Alpha particles, really easy to shield. What would be a great way to stop alpha particles from hitting my body? Okay, well, I could use a piece of paper. That would be a very effective block. Or I could do something novel like wear clothes. That pretty much stopped the alpha particles. Now I say wear clothes. The porosity of this stuff is probably enough that alpha particles could get through. There's holes, right? But alpha particles are easy to stop. Beta particles, alpha particles are easy to stop because they're relatively massive, 2 protons, 2 neutrons. Beta particles, being just an electron, are harder to stop. For beta particles, I might need myself a piece of lead or something to block it. Gamma particles, the electromagnetic waves, those are really hard to stop. That's where you need the real shielding. So we have different penetrating powers, and they're named in order of those penetrating powers. So alpha is most penetrating, then beta, then gamma. I'm sure you will get at least one, and probably more than one, question that deals with radioactive decay and time. That is things like how radiometric dating works, what a half-life is. So make sure that you remember, half-life. After 2 half-lives, how much remains? Yeah, 25%. Because it's 1/2 of 1/2.
Oh,
Right? Without having taken the class, you're likely saying, well, 1/2 plus 1/2 means it's all gone. But it's not 1/2 plus a half, it's 1/2 of a half, so 1/4 remains. And so after 5 half-lives, you have 1/2 of 1/2 of 1/2 of 1/2 of 1/2. Or, that would be 1/32nd remaining. So make sure you can do those calculations. Remember, you had a homework problem where you went from, 80 to 5, and then it was, so you went from 80 atoms to 5 atoms, I think it was, in like 8 hours, and asked you what the half-life was. So you had to go through and say, okay, how many times did I cut it in half? 80 divided by 2 is 40. 40 divided by 2 is 20. 20 divided by 2 is 10. 10 divided by 2 is 5. So that was 4 half-lives, 4 cutting in half. So 8 hours is 4 half-lives. So 8 divided by 4 gave you 2. So make sure you can do that kind of thing. Last thing in chapter 13 was nuclear fission and fusion. Fission and fusion are both things that, to naturally occur, you need to have a lower mass after the event. And that starts to get confusing because we tend to think a proton has a fixed mass. But Einstein gave us the equation E equals mc squared, that the energy that something has relates to its mass. And so when we form chemical bonds, we actually are converting some mass into energy. And so the mass drops. And much more so when we talk about nuclei. Nobody ever measures mass differences for chemical bonds. But for nuclei, the energy is so strong holding the nucleus together that we have a measurable difference in the mass. So if you measure the mass per nucleon is just a word that means particles in the nucleus, i.e. protons plus neutrons. The mass per nucleon is the lowest for iron, which means iron has the most stable nucleus. Protons have the least mass in iron. And so either fission or fusion will release energy if you're moving toward iron. So that means if you're doing fusion, making two things merge together, if the two things are less than the mass of iron and form something closer to the mass of iron, you're going to release energy, and that's going to be then what we call exothermic. Exothermic releases energy, X out. Energy goes out. If you want to make a power plant, you need something to be exothermic. You need something that's going to release energy. But of course, if I just take 2 hydrogen atoms, I can't just make those hydrogen atoms fuse together. How do I make them fuse together? I have to have 2 things. Number 1 is I have to have a high enough pressure that there's a reasonable chance of 2 of them coming head on toward each other. Right? Think about it this way. If it's just Brandon and I, and there's no tables here, and we're walking around this room blindfold, it's going to take a while for us to hit. And if we go out to the football field and we do the same thing, we might never hit. Right? So there's no chance of us having a reaction. But if we take the entire student body and we put them on the football field and do the same thing, we know there's going to be a lot of collisions. So having pressure is one of the ingredients you need to have fusion. The second one is the I thought I heard something after that. The nuclei have a positive charge. What do positive charges do when they come close to each other? They repel. So once again, if we go with Brandon and me, if we come toward each other and Brandon doesn't want me to hit him, he'll put his arms out and catch me and stop me, right? But if I come really, really fast, I'll have enough energy to overcome his attempt to hold me away and we'll still have a collision. The same thing occurs with nuclei. You have that repulsive force from the nuclei pushing them apart. But if you have them moving fast enough, they will have enough energy to overcome that repulsion. How do we measure energy in something like an atom? I measure its speed. Temperature. Is that what you said? Almost, okay. So we have to have high temperature and high pressure to make fusion occur. So it doesn't just occur all around us because you have to have those ingredients. But if you have those ingredients and it's something like two golds, the golds aren't going to stick together because that would be a higher energy state. You'd have to have a really large amount of energy to get those things to stick together. You actually can do it at super high energies. Where does this occur? In supernovae. In a supernova, which is the collapse of the core of a supermassive star, you actually do have fusion of things that make elements larger than iron. That's the only place things larger than iron are made. So everything that we have that's larger than iron, things like gold, it was made in a supernova in the collapse of the core of a supermassive star that was dying. So yes, we have stardust. Everything that's bigger than helium is technically stardust. So we're made of stardust. Okay, so nuclear fission is breaking two big pieces into smaller pieces. Once again, you have to go toward iron to have it release energy to make it useful. Now we can use this for good or for evil. For good, power plants. We have nuclear fission power plants. For bad, bombs. You may disagree with me, but I'm going to assert that it is a given that bombs are bad, that blowing up people is bad, especially when you're blowing up people and leaving remains that will be making it hard for life for a while, leaving radioactive material. So this is something where scientists have to be responsible. By the way, if you're curious, you guys know Angela Merkel came and visited President Trump this last week. She has her undergraduate degree in quantum physics and her doctorate in quantum chemistry. And so this is actually an area where she is an expert in the world. So moving from there, chapter 14. Hey, we're on the third chapter and we're doing okay. Because those first few chapters were the longer ones. Ones after that, not as long. Elements of chemistry. We start talking about things like, what is a chemical? And my basic definition of a chemical is anything that has atoms bound together. Some are natural chemicals, some are synthetic. So what's a natural chemical? Water is a natural chemical. It occurs naturally. So is whatever that stuff is that makes you itch and poison ivy. It's a natural chemical. Natural doesn't mean it's good for you. It just means that it occurs in nature. Synthetic means man-made. So a synthetic chemical, I assume my wife buys me polyester shirts. I don't know. Could be time. But polyester is a synthetic material. It's something that was synthesized by people in a lab. Is there something inherently good or bad about being synthetic? No. The origin doesn't matter. It's the chemical itself that makes a difference. So then we have things like molecules. Molecules are, of course, essentially the same thing as a chemical compound. If I say H2O, that's a molecule. It's three atoms bound together. If we were to use the naming scheme, right, be able to name simple compounds, how would we name H2O? We have to use the prefix di and mono because we can also have things like H2O2 or OH. And so we need to differentiate them.
Do many molecules make up chemicals? Is that how it works?
Well, no. Molecules are chemicals. One molecule of water is a chemical. Right. My wife, I said, uses it in a completely different way. To her, chemicals means only harmful chemicals. And in fact, she further tends to think that means only synthetic harmful chemicals. She tends to think plants won't make things that are bad. And then when I point out things like poison ivy or whatever, she's all, well, I'm not talking about those natural chemicals. But this being a science class, we're trying to make sure we have the basic understanding of these things. So you know how to name that dihydrogen monoxide. We change it from oxygen to oxide. And the di because of 2, the mono because of 1. An element. What's an element? One type of atom. So if you look back there at the periodic table, that lists all of our elements. That's why it says periodic table of the elements. And so aluminum, it's an element. If I have pure aluminum, it's elemental. If I have aluminum that has other metals mixed with it, it's no longer elemental now, it's an alloy. And an alloy is a type of, it was a type of homogeneous mixture. So the mixtures, there's in another chapter, it's covered in detail, but I'm going to cover them right now. A mixture is where you have at least 2 types of molecules. And if those 2 types of molecules are indistinguishable, that is, you can't say, oh, there's this type and there's this type, then we say it's homogeneous. If you can tell the difference, then we say it's heterogeneous. Hetero, different, homo, same. So an example of a homogeneous mixture is milk. Homogenized milk, so it makes it easy. What makes it homogenized? Well, if I remember right, they take aluminum wire and crush it into this little thing that, for all the world, looks like a Hershey Kiss. I saw one sitting on my dad's desk, and I wanted to eat it, and I picked it up, and, well, no, that's not going to work out for me. And then they force the milk through at high pressure. And what that does is it breaks up bigger things into smaller things so that they're indistinguishable. So you don't have chunks of anything. And so you have little things of milk fat that are suspended in water. So we call it a suspension. But you can't tell that unless you look at a microscope, so it's a homogeneous suspension. Whereas an example we had in class, pizza. Well, you can tell the difference in the mushrooms and the tomato sauce. So that's a heterogeneous mixture. Of course, nobody thinks of pizza as a chemistry thing, but it was an example. So we have those kinds of mixtures. An alloy is a mixture of metals. That is, you have metals that, because of the unique metallic bond, you can substitute one metal for another and it doesn't care. Compound. Uh-oh, my brain went blank. Go ahead. What was it? Oh. Say it louder.
2 or more.
Okay. Yeah, a compound is where you have 2 or more elements mixed together. So H2O is a compound because you have H and O. Whereas element is just pure. So oxygen, O2, it's a molecule because it's 2 oxygens bound together, but they're the same type of atom, so it's still elemental. Thank you for straightening me out there, Jocelyn.
So H2O is a compound,
Yes.
a molecule,
Yes.
and a chemical.
Yes. Yes. Lots of names and lots of overlap. Okay. Then we had the final thing here, physical properties versus chemical properties. Chemical properties are, if you change chemical properties, you actually change the bonds. So an example of a change in chemical properties is when you have acid and calcium carbonate, and the calcium carbonate then starts producing gas. That gas is producing, what's it, carbon dioxide? Is a different compound, different molecule. So you had a chemical change there. Whereas a physical change, you don't change the molecules, you just change something about how they're organized or behaving. So when you freeze water, you change from the liquid state to the solid state. That's a physical change. It's still H2O. Same chemical, but just different properties because you've changed its physical state. Chapter 15. I told you, quicker going to these later ones. Chapter 15, we learned about how atoms stick together. Bonding is what we call it when they stick together. And so we learned about a number of different types of bonds here. Excuse me. Before we got started, we learned first about the Lewis dot notation, or it's more commonly called these days the electron dot notation. Yes, it was invented by a gentleman whose last name was Lewis. So the dot notation is simply a way of indicating how many valence electrons an atom has. So if I take something like silicon, silicon's in the third period, the 14th group. And so I looked there and we learned, okay, group 1 has 1 valence electron. Group 2 has 2 valence electrons. Skip the transition metals. Group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Now, how many electrons does a neutral silicon have? How many? Okay, it has 14 electrons. It has 14 protons, and if it's neutral, it'll have the same number of electrons. I don't remember what's the number up in the top right corner there for silicon. Okay, then the bottom center. Just the first two. Okay. So a typical silicon atom would be 1428. You can't always do that, actually. If you look at bromine, I think the number down there is something like 81. 79, okay. It doesn't actually have ever 79 electrons. It's a mixture of about equal amounts, 78 and 80, giving you an average of 79. But if you read this, that there, what do we call that 14? It's the atomic number and that tells us it has 14 protons in the nucleus. And what do we call the 28? The atomic mass. And that tells us there are 28 protons plus neutrons. If I take the difference in those two, protons plus neutrons minus protons will tell me how many neutrons. And if it's neutral, it'll have the same number of electrons as it has protons. So silicon has 14 electrons, but how many of those are valence electrons? Correct. So 14 electrons, 4 of them valence. And so for our Lewis dot structure, we'd put the silicon, and we use 4 corners for our dot structure. So the first 4 just go 1 in each corner, and by convention, we usually start at 3 on the clock, go 3, 12, 9, 6. So that's the electron dot structure for silicon. If I was going to do its neighbor, aluminum, what would aluminum's dot structure look like? How many valence electrons does aluminum have? 3. So where do I start? At 3 o'clock on the clock, and then where do I put the next one? And the final one? Over here at 9. So that would be the way I would draw the electron structure for aluminum, using the Lewis dot notation. Why is this useful? To help us see how bonds work. We learned about these bonds here that are marked ionic and down. An ionic bond occurs when we have something that's really electronegative, it really wants an electron, and something that has a low electronegativity doesn't really care. An example would be hydrogen and chlorine. Hydrogen and chlorine, the chlorine really wants an electron, the hydrogen doesn't really care. So the chlorine goes zoink and grabs the electron from the hydrogen, and then the chlorine has an extra electron, the hydrogen has one missing, but if we show the bond with the dots, we can take the chlorine, and now I'm going to switch where the dots are to make it bond. We can take the chlorine with its So I switched it by putting the lone dot on the left side. And the hydrogen with its dot there, and those two there are what we would say is forming the bond. Now what really happened was the electron is mostly spending its time with the chlorine. So that's an ionic bond. When the electron goes to the chlorine is negative, the hydrogen is positive, opposite charges attract, and it's held together. And actually, generally stronger bond is the covalent bond. So covalent bond is the kind of bond that you form between, let's say, carbon and oxygen. So carbon's like this. How many bonds is carbon going to want to form? 4, because it has 4 lone electrons there. If I take an oxygen, the oxygen and the carbon will come together right now. Too far. That'll do her. And here, because carbon and oxygen have similar electronegativities, they're just going to share those 2 electrons. And so the carbon says, got a pair here. The oxygen says, got a pair here. The oxygen still has 1 more that it wants to bond. The carbon has 3 more it wants to bond. So we could, for instance, now fill it up with hydrogens. Hydrogen here, hydrogen here, hydrogen here, hydrogen here. And now we have 8 around both the carbon and the oxygen. Each one feels like it has its complete outer shell. I said it feels. Yes, they don't feel. Okay. It has a lower energy state because of that configuration. Each hydrogen says, hey, I've got my pair. So it is also in a lower energy configuration. So that's a nice stable compound. What's the name of this compound?
This one?
Okay. One option would be quadrohydrogen, or actually not quadro, tetra. Tetrahydrogen monocarbon monoxide.
That's not it.
That's not it. The actual name is methanol.
That's what it said.
We have that all there because it's an alcohol. It has the functional group of the alcohols, which is this right here is the functional group of an alcohol, a carbon with an OH bonded to it. The meth means that it's 1 carbon. So that's methanol. All right, quickly going through the bonds. We did the ionic bond. The covalent bond is a shared electron that we just talked about. Then we have the more interesting ones. Ion dipole. I have an ion. Let's say I have an H plus floating around. And I have a dipole, something like a water molecule. Water molecules have an electric dipole moment. That is, you have a positive side and a negative side. The oxygen is negative, and we have a positive hydrogen out there. The positive hydrogen says, hey, there's a dipole, there's a negative, positive, negative attractant that sticks on, and then we have the hydronium. So hydronium is an example of this, where we had a dipole that attached, a dipole to water, that attached to an ion, the hydrogen, to make a new molecule that's not a neutral molecule, right? It has a net charge. Dipole would be something like 2 water molecules being attracted to each other. Now this dipole bond, compared to the bonds that hold atoms together, a molecule is weak. But compared to the rest of these, it's really strong. And so water has dipole bonds. We call them hydrogen bonds if a hydrogen is part of it. So technically people will say it's a hydrogen bond, that's a type of dipole. Where the hydrogen of one molecule is attracted to the oxygen of another molecule. And so if they cool down so they're not moving around rapidly, they will start aligning themselves so that you have each hydrogen is weakly attracted to the oxygen of another molecule. So you start making things that are, here's my O, my H, and then you'll have, this is making a weak bond to an O with an H and an H. And this is making a weak bond to an O with an H, that's not an H, and an H, and so on. And that's why water actually expands when it freezes, because the organization that occurs to make it so you can make these hydrogen bonds actually makes it spread out. And that's very important, as we talked about in physics, to the fact that we can have life on Earth and we don't freeze. Dipole was the hydrogen example I just did. A dipole-induced dipole. If I have a dipole come by, that dipole has a positive and negative side. And if I have an atom that's not polar, as the charge is symmetrically distributed, when this comes by, the positive side will attract electrons and distort the formerly non-polar molecule to make it polar. But once it's been distorted to make it polar, then you can have a dipole-dipole interaction. So we call that a dipole-induced dipole. The weakest of all of these is induced dipole. You have two nonpolar molecules. As long as they stay away from each other, they're just fine. They get close to each other, and each one repels the electrons from the other one, making it so each one has a negative side and positive side, and then they rotate around and stick together. That's a really weak type of force. So that's the induced dipole. Now, metallic is the unique one. Metal atoms, when you put them together, the valence electrons, right? A transition metal has two valence electrons, and then it has the ones that are one level above filling in. And those two valence electrons generally are pretty loosely held. So when you put the molecules together, or the atoms together, those electrons just kind of float around. We call them conduction electrons. So you have positive nuclei now because they've given up those electrons. You have the negative electrons, and you have the electrons hold the solid together. But because it's not a molecule holding to another molecule, you can easily shift one type of metal for another type of metal. That's why alloys are easy to make, because you're not forming an actual bond between the nuclei. It's the electrons holding them together. Okay, chapter 16. Okay, I already talked about this entire top part. Solutions, when you mix things, the lower concentration thing is called the solute. The greater concentration thing is the solvent. Them together is the solution. So you need to be able to calculate the molarity. That is the number of moles of solute divided by the liters of solution. And that introduces the word mole. The word mole here is not referring to a rodent. It is referring to a specific number of molecules. And that number of molecules is the number of molecules that will make, if you have that number of molecules, the mass will be equal to the atomic mass in grams. So for instance, if I take helium at the bottom there, it says 4.00, I got to get really close to here, 4.00260. And so if I have a mole of them, if I have 6.022 times 10 to the 23rd helium molecules, it will have a mass of 4.00260 grams. That's what a mole is. So it's basically a conversion factor for the difference in the gram and the mass of a proton or neutron. So it's just counting numbers of molecules. We talked about how soaps and detergents work. Soaps and detergents effectively are the same thing. The difference is a soap is you took a fat, you put it in lye, and you create a chain of hydrocarbons, and then at the end of that chain of hydrocarbons, you have a polar molecule. The polar molecule will make a dipole bond with water. The nonpolar will make an induced dipole bond with grime. And so what you end up having is one end of the soap will attach to grime, the other end attaches to water, allows the water to pull it free. What's the difference in soap and detergent? The detergent is harsher. The detergent has a more polar end. It works more effectively at attaching to water. Water softeners. In our water, we have impurities, things like calcium carbonate. And that calcium carbonate can be precipitated as a rock. And so as the water goes through our pipes, we have slow precipitation on the inside of the pipes, building up a rock layer inside the pipes, which we tend to consider uncool. So to try to avoid that, we do things to soften our water. Softening the water is removing the calcium from the water. And that's done by trying to replace the calcium with sodium. And so we had some pictures in our textbook of the process by which you have little resin with a bunch of sodiums on it, and calcium will come and displace the sodium, and then the sodium goes where the calcium was, but it won't make the rock precipitate. For the water purification, make sure you look in the textbook. That's a little complicated to try to cover here in class once again. But make sure you look at the water purification process, how we try to make water that's not going to be contaminating things out of waste. Okay, chapter 17. Wow, I'm not going to get to the last two chapters. Make sure you can balance chemical reactions. Chemical reaction shows reactants and products. Reactants is what you start with. Products is what you end up with. We're not transmuting, right? We don't have radioactivity going on here. So we should have the same number of each type of atom on the product side as we had on the reagents or the reactant side. So when you go through, you just have to do your math, look and say, okay, well, I only have carbon appearing in one molecule on the left and one molecule on the right, so I can see what the ratio has to be between those two, and then you work your way up. And really practicing balancing equations is the only way, I think, to develop that skill, because it starts to become an intuitive process instead of a mathematical process after you've done it a few times. I already talked about this. That was with the moles. Let's go to activation energy first. Activation energy is the energy necessary to make a reaction occur. I might have a perfectly good exothermic reaction. It's an exothermic reaction because I can measure the total bond strength in the reactants and the total bond strength in the products. And if the total bond strength in the products is greater, that means I'm holding it together more strongly. It's a lower potential energy, and energy will be released equal to the difference. But even if that's the case, the reaction may not occur because you have to make the reaction start. And oftentimes you have to separate some molecules before the reaction can occur. And it takes energy to separate them. So the activation energy is the energy you have to put in to make the reaction start. And if the reaction then releases more energy than you put in, it's exothermic, it's giving off. If the reaction releases less energy than you put in, it's endothermic. You have to put energy in. So the activation energy is the energy you have to put in to make the reaction start. So we had graphs with things like this. The energy you had to put in to start is this activation energy. And then you take the difference from starting to ending, and since this went down, it's exothermic. Now we can overcome the activation energy with catalysts. Catalysts are atoms or molecules that will lower the activation energy for a reaction. Now those catalysts may be shifted and do something in the middle of the reaction, but by the time you're done, they'll be back to how they were when you started. So we had an example where we had sulfur. In the middle stage, the sulfur became sulfur dioxide, but then in the end it was back to sulfur. So sulfur was a catalyst that lowered the energy to get the reaction going, but what you put in to start with, you end up with at the end. Okay, chapters 18 and 19, we just finished acids, bases, reduction, oxidation, and you just look at these on Moodle.
I'll look at it on my phone.